And that's going to show me a sequence of autonomous system numbers and tell me how my router thinks to get to that prefix. Which organizations am I traversing to get there? So the first one is the shortest path because there's only one AS in the AS path, 32934, which happens to be Facebook. So that's the ASN of Facebook. And what this tells me is that OpenDNS, or at least this router, is directly connected to Facebook over the Internet Exchange. So obviously, this router is going to prefer that path in normal circumstances. Then the alternative, so let's say that link goes down. The alternative is the green one. And you can see there are 3 ASNs in that path. The one on the right-hand side, again, is the same as the one above. So it starts with the Facebook AS, so that, again, is 32934. Then it shows 1221 and 4637. So this tells me that my router is connected to 4637, which is, in this case, Telstra International, which is connected to 1221, which is Telstra Domestic, which is a different organization, which is then connected to Facebook. And then the last one starts with 2914, that's NTT. NTT sends it to NTT Australia, which sends it to Telstra, which then sends it to Facebook. Anyway, so this shows you that the router has multiple options, and it determines its path based on the AS path length by default. So there's all kinds of interesting things that you can infer from this by just looking at an AS path. You can see who originated the prefix by looking at the rightmost ASN. You can see how we learned it by looking at the leftmost one. And then you can learn something by the relationships. By looking in this path, you can see that, and in this case, Facebook is connected directly to Telstra, probably pays Telstra for transit connectivity, and the same with NTT. So there's all kinds of interesting things you can do. Okay, so I think that's sort of the introduction into routing on the internet, how that works, and what that looks like. So now let's take a look at some examples where it didn't quite work as expected, at least not by most of us. So let's talk Bitcoin. I'm sure we already talked quite a bit of Bitcoin. Bitcoin's popular nowadays. Everybody wants to be in Bitcoin. There's lots of money to be made and lost, depending on when you got in. But there's also lots of Bitcoin mining farms. And this is an example of a company called Megabit, Megabit Power in Washington State. They literally have thousands and thousands of boards working on mining Bitcoins. And altogether, they're trying to solve this complex mathematical puzzle. And every now and then they find the answer and they get some reward for it. Lots of people do this. This is an example of a 5 megawatt farm in Thailand. Didn't work out so well for them. It caught on fire. Millions of dollars in hardware went up in flames, and apparently they had no insurance. But either way, I think what I'm trying to say is lots of people are trying to get into this, but not all of us have the money or resources to actually start a Bitcoin farm. So what you do when you don't have your own data center, your own hardware, well, you can do the same as we all do in our enterprises or in home. You go to Amazon or you go to DigitalOcean, and you use their CPUs to do the calculations, and as long as the rental price is lower than the money you can make with it, it all works out. And this is sort of where this story starts. A little bit about Bitcoin. I am by far not a Bitcoin expert, but I think in the simplest form what happens is when a Bitcoin miner comes up, it basically joins a Bitcoin pool. Bitcoin pool has a pool server and basically gives out assignments and gives you the credits for it. So this attack was officially initially detected by Dell SecureWorks, and it's something that happened between 2013 and October 2013, May 2014. And what happened here was when miners would come up and register with the pool server, the pool server would send a redirect to another server and it's part of the protocol where you can basically, it's part of a load balancing mechanism. You can say, well, you shouldn't be talking to me. You should go and talk to this guy because I'm too busy or whatever. Now the question is, so that other server was controlled by the attacker. So now the question is, how was he able to initiate that redirect? Well, what he did, he was basically hijacking the IP addresses of the pool servers. So these pool servers in question were running in Amazon, DigitalOcean, OVH, all your standard hosting providers. So let's say that Amazon typically announces their prefixes in /16s. He would find out a pool server isolated, which was a single IP address, isolated to a /24, which is a more specific block, has about 256 addresses in it. It would then announce that particular range of IP addresses and saying, if you want to go here, you need to send it to me. And because there's no, it's all based on trust, everybody on the internet who saw that BGP update started believing that. And as a result, all traffic for that /24 was now being redirected to, this other server, or at least the network he controlled. At that point, he initiated this redirect, and the miners would go to yet another server, which is where sort of the interesting thing came in. The redirect, or the BGP hijack, was only visible typically for a few minutes, 2, 3, 4 minutes or so. Fairly short, but it was enough to, to find a fair amount of miners initiate the redirect. The miners would still be sticky to that other server and mine for days or weeks, and basically mine but not get a reward for it. So if you look on the forums, several people after a few hours or days find out what happened. So this was a really interesting case because it was sophisticated on multiple levels. And not only was it, it was combining the Bitcoin stuff with BGP stuff, but he was also trying to hide what he was doing using a technique called AS path spoofing. So remember the path, the range of ASNs. He was actually, trying to change that and lie about it, so interject other ASNs. So it was very hard to determine where the actual attack came from. So this went on for a few months. Affected several cloud providers, again, DigitalOcean, Amazon, all the ones that we all use for different purposes. Actually, it was a Canadian thing as well. So we've determined that the network in question, who was announcing these things, because the thing is, we can't go home tonight and try this. Like, we need to have access to a router, which is BGP. And at that point, you need to be connected to another provider, or even better, to an internet exchange. So an internet exchange, has a new term, is basically a large switch where lots of internet providers connect to, and then you have sort of this direct connection with all of them, and then you can set up this BGP session with them. Transit providers are providers that are very large providers, like Level 3 or NTT, or more regional here. Let's think about Thales and Bell and Shaw, and you pay them to provide transit. They typically are pretty strict in what's called BGP filtering, is in they have a list on their router and say, okay, I know you are OpenDNS or Google. You're only allowed to announce these prefixes because I know those are your prefixes. I'm not going to allow you to announce anyone else's prefixes. But that's a lot of administrative work. So if you are on an internet exchange where you typically peer with hundreds of other networks, and those IP addresses change all the time, people have just basically given up on that. It's like, I'm not going to filter that. That's way too much work. I'm just going to trust it. If you're announcing 20 prefixes today, I'm going to allow you to do 30. And they just have sort of a hard cap. And that's why this attack really works well on, for example, the Toronto Internet Exchange, or any internet exchange really. But this happened on the Toronto Internet Exchange. So this was primarily affecting peers that were connected to the Toronto Internet Exchange, who are either peering with this organization or with what's called a route server, which is really a proxy for BGP announcements. In summary, Dell Secure Works guesses that this, or estimates that they made about $83,000 with this. We verified that there were at least 51 prefixes hijacked over the course of a few months, which affected 19 unique autonomous systems. And you can see a few of them listed here, but I mean, none of that was really targeted. It just happens to be where all these guys are, right? So this is a really interesting case where people were using BGP hijacking to try and make a good buck. So let's take a look at another example. Censorship. So the internet is no longer truly open. We all like to think so, but every now and then there's quite a bit of censorship going on, and in certain parts of the world this happens more than others. Turkey is this particular example, but we all know about China. And several other countries. So this is actually a really interesting case because it affected our network directly, OpenDNS, but also Google and Level 3, who also run large OpenDNS resolvers. So what happened here, it was election time in Turkey, so March 28 till March 30, which is about exactly a year ago now. And there was some stuff on YouTube and Twitter that the Turkish president didn't like, and basically ordered his government to block both YouTube and Twitter for the whole country. So then you as a techie are ordered to do this, and you try to figure out how do I do this for a whole country, right? So there's different ways of doing it. But in some cases, especially cases where a certain country only has 1 or 2 ISPs, and they happen to be controlled by the government, definitely makes it easier. And it happens to be the case in Turkey. Turkey has Turk Telecom, which is the largest provider there. And obviously, most people there use the Turk Telecom DNS services, right? So they said that we can do that. So what they did was they basically in their DNS service add a static entry. So if you want to go to YouTube or Twitter, this is the IP address, which obviously wasn't really the IP address of YouTube and Twitter. And as a result, your computer was trying to connect to something that either didn't exist or was something that was controlled by the Turkish government and says, hey, you're not allowed to go here or something like that. So, succeeded. Engineers happy or not, at least they did what they had to do. So that was good for them. But pretty quickly, these images started appearing in the mainstream press. So as a DNS geek, and most of you maybe, like you see IP addresses spray painted on bus stops and walls. That's pretty cool, right? We don't really see that every day. So we're like, oh, that's cool. What happened was people figured, well, if we use something like OpenDNS or Google or some of the other free open resolvers, we are able to bypass the censorship. So people started using this like crazy, and at OpenDNS we saw a huge spike in uptake from users from Turkey, and I'm sure Google saw the same, and some of the others as well. So citizens of Turkey happy, we are now able to bypass the government censorship. We rule, awesome, right? Turkish government not so happy. Within a few hours, we noticed all traffic from Turkey dropped off. There was basically 0 traffic left. What happened was they had now null routed all traffic to some of these IP addresses, popular open resolvers like Google and OpenDNS. Well, that sucked, and but they pretty quickly on realized that the collateral damage is pretty significant, because not only did they now null route traffic to our name servers, they now also broke the internet of, I don't know, a very significant portion of the country, because everybody had changed their DNS servers to us, and now I was like, well, I don't know, I type in Facebook and it doesn't work, or I type in CNN or whatever they're visiting, didn't work, and we all know this, like DNS doesn't work, or I don't care, I don't know, internet's broken, right? So they had to sort of undo this because people couldn't work anymore, stuff was broken. So pretty quickly on, they undid this. They realized that hammer is a little bit too big. So we're happy again. We see traffic, all awesome. Next day, though, they did revise their setup, and so that's sort of the final setup where they came up with. They had now configured a server or a set of servers with the same IP addresses as OpenDNS and Google's 888 and so on and so forth, a few others, and they started inserting new BGP announcements. And this is an example of that announcement. So they started to announce, for example, 8.8.8.8/32. So this is a screenshot from when this happened. I took it. It is normally if you want to go to 8.8.8, it's a /24 route. That's sort of the accepted minimum route you can announce. So that's the normal healthy route that we would be looking for, that I know Google really announced. But now we're seeing a different route, and in fact the AS path is empty, which means that it's locally originated. So this is the proof that they inserted a new BGP announcement, a new route, and they set the next hop to a server that they controlled, and they were in fact answering DNS queries. It was actually a DNS server. But now again, they had applied that same mechanism as they did initially. If you type in YouTube or Twitter, they would give them back an IP address that obviously wasn't YouTube or Twitter. And you can see an example here. This is from a tool called RIPE Atlas. It's basically a very large measurement project. So we did a DNS lookup from within Turkey, which is the one in orange, using 888, for example. You can see the IP address that was returned, 195.175, blah, 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 which is an IP address controlled and owned by Turk Telecom. So there's a clear proof that this is not the real YouTube server. You were being redirected to this IP address if you were in Turkey, but it wasn't actually YouTube. And then in green, you can see an example of what it would actually supposed to look like, where it returns a set of YouTube IP addresses. So in summary, the Turkish government has now achieved censorship using DNS, and they figured out a way to also censor DNS servers that they don't actually control. Google, OpenDNS. So this is all really, really scary stuff. Fortunately for us, about 2 days later, this was done with. A lot of pressure on the background, but eventually it got solved. But it does show, how vulnerable the system really is, because there was very little we or even Google could do. I mean, just insert that announcement there, and it's there. You can't just delete it. So that is an example for BGP hijacking for censorship and setting up a man in the middle again. Okay, another example, spamming. So what's interesting about spamming? I mean, spam has been around forever. We've talked about it a lot. What can we say about that? Well, turns out there was actually a significant operation going on last year where spammers were using BGP hijacking or BGP as a technique to solve their biggest pain. The biggest pain for spammers, as we all know, is finding clean address space, right? So as soon as you start spamming, within a few minutes or hours, it ends up on the blacklist and you can't really use it anymore. It's also really easy to track, who was doing the spamming. So if, maybe you don't care about that, but sometimes, that server, maybe it was owned or whatever and taken offline, so on and so forth. So the biggest problem for spammers is finding unused address space or clean address space. As we all know, we're running out of IP address space, right? IPv4 it's almost gone. We need to go v6, et cetera, et cetera. But there's actually large squads of IPv4 address space still available. It's been allocated to organizations, but many organizations are not actually using it. So if you look in the BGP table, you'll see, oh, it's allocated to the US DoD or even the Canadian Forces or, I don't know, GE or whoever. Some of these really large organizations have large spans of address space that they're not using, at least not publicly, maybe internally. But it's not visible in the global BGP tables. So what these guys did was basically start searching for that. Just loop through it. 1.1.1 is available, 1.2, and etc. And so at some point, they found literally thousands of networks that were not currently being announced. And they said, okay, I'll just claim ownership of that. And I'll start announcing it, configure it on my server, and now I have a new IP address. I got a /24, a /16, or whatever. I loop through it, start sending spam, and once I'm done, I'll just use the next one. I literally had thousands of networks to use for this. Very scary stuff. So that's what they would do. So let's take a look at what that looks like if you visualize it. We spent a lot of time on sort of fingerprinting this and figuring out what exactly happened. So this is an example for one ASN, but we found different other ASs that all had a very similar fingerprint. Initially, we assumed they were all different operations, sort of using the same technology. Later on, we found out there was actually actually two organizations behind it. But what you're seeing in this graph or in this visualization is basically on the bottom line, you see the timeline. On the vertical line, you'll see the basically list of prefixes. And the green line is the lifetime of the announcement of a prefix. So what you can see here is a very clear fingerprint where spammers would start to announce the address space 8 prefixes at a time for a few hours, stop it, and immediately start a new batch of 8 prefixes. And sometimes that would be a few hours, sometimes it would be 2 days, depending, I don't really know what's going on, but if you visualize it, it's very, very clear that a new cycle of announcements would start. So we contacted, well, not the ASNs involved, not the origin ASNs, but sort of their upstream providers and say, hey, do you know what's going on here? Like, it's very uncommon for a network to constantly start announcing new prefixes. Typically, you get an announcement, you get a prefix allocated, you announce it, and you use it for years, and then maybe you bring another one in, but definitely not for hours at a time. Like, nobody really owns that many prefixes that you can do this on basically for weeks or months. So we started talking to them. We said, hey, why are you announcing? Why are you accepting these prefixes? You remember we talked about filters. Well, they said we have an automatic filtering system in place, which is called sort of a WHOIS system for routing health. And they were using RADB, which is one of the more popular systems. And so we're just automatically generating these filters. So as long as the customer, the spammer in this case, would add a whois entry for this, it would just work. And then we started a little bit harder. So, well, why are they announcing all these prefixes all the time? And they would say, well, if I look on my file and I talk to the customer, they're what's called a DDoS mitigation company. So they're mitigating attacks for different customers, which is really the only reason why something like this could happen. But then we would go back and say, well, who are they mitigating attacks for? All these prefixes haven't been seen in years. Are they mitigating attacks for ghosts or whatever, right? So that basically, that really got their attention. And they helped us a lot with looking at NetFlow data, PCAP data, and it indeed showed that 99% of the traffic was basically SMTP traffic. In fact, it was almost 100%, which is actually interesting, because where did all this control traffic go? Where were the DNS lookups? Where was the SSH traffic or whatever? It was basically missing. It sort of leads into a different conversation, but there must have been definitely sort of another backend system that was doing all that kind of stuff. This is an example of the whois entries that they were adding. So you can see the prefix, there's a description, and then there's the important part. There's the origin AS. So they basically said, I am hereby authorizing myself to announce this prefix from this origin ASN. And then there's the maintainer object, which is basically sort of the owner or the guy who added this. So this is good and bad because now we knew, oh crap, they actually figured out how all this works. They're smart guys. But at the same time, we can now look at what other routing objects have they added. So for this particular AS or even by this maintainer. And indeed, we saw literally thousands of route objects. Typically for prefixes that were announced in the past by the same ASN and we used to send spam, we could validate all that and it was like, okay, now we validated it. The cool part was there were also route objects in there, whois entries, for prefixes that weren't announced yet. So it also provided us with a looking glass into the future and we could start predicting what they were going to use next. So really cool stuff. Again, we worked with the providers and got a lot of this stuff shut down. This is an interesting graph from another provider. This is, I believe, a Russian one. The Russian one's really interesting. They would start strictly at 9 a.m. Moscow time, always. That was really cool. And they also take vacation. So there's two distinct gaps in this graph. I'm not sure if you can see it. But it's basically over Christmas and New Year's. So that's pretty cool. So you can definitely see that there's humans behind this stopping and starting these operations. So while we're talking about spamming, we've all heard about Spamhaus and how they try to, do something with this spam problem. Their reputation among some networks is somewhat dubious. Not everybody likes them. They do good work, but sometimes their hammer is pretty big. So they tend to make a lot of enemies, especially sort of in the world of spammers and the more gray areas of the internet. So this is about, I think in 2013, Spamhaus got into the news because there was the biggest DDoS on the internet ever, and it was significant. It was 300 gigabits of traffic. This is, remember, 2 years ago. So that's a fairly significant DDoS, supposedly the biggest up to that point. And that's not something you want to deal with. Spamhaus at that point moved to Cloudflare to help them with that, and lots of ISPs were scrambling to make this all work. And sure, there were a lot of bits, but it was really a blunt hammer, a big cannon to try to take Spamhaus offline. What didn't get as much attention was at the same time, the guy who was doing or supposedly behind this attack or the DDoS also started to announce a more specific BGP announcement for one of the Spamhaus RBL servers. And you can see that in this screenshot where they were announcing 204.16.254.14, which at that point was an RBL server. It was running a DNS thing, and basically you feed it an IP address and say, is this a spammer or not, or can I trust this? And it basically says false or false or positive result. So what happened was this was announced over the Amsterdam Internet Exchange. People connected to the Amsterdam Internet Exchange, which is the largest internet exchange in the world, so there's hundreds of organizations there. We're now routing to this new BGP route. So it wouldn't end up on a server controlled by Spamhaus. It would end up on a server controlled by this guy. He had actually set up a DNS server and was basically giving back positive replies for everything. So rendering the Spamhaus servers unreachable, because some of these guys that noticed this said, well, my spam level went up like crazy, and some of these are obviously not spam. So as a result, they had to shut down or deconfigure the Spamhaus configuration in their mail servers because it was unusable. So that's sort of another, DOS service really, and it was another factor as part of the larger DDoS. And again, a really interesting case, how you can basically render something unusable or just another man in the middle, really. So let's talk a little bit about some of the, I guess, larger scale hijacks. So what we've looked at right now, they were typically pretty targeted, trying to figure, or specific purpose. Some of these things are targeted. We've looked at the Bitcoin one, we've looked at the Turk Telecom one. There's really, certain things that they're trying to achieve there. Unfortunately, BGP been around a while, and there's been more than one of these accidents. Sometimes they're just plain accidents, like someone mistyping something on a router, and you're forgetting a digit somewhere, and all of a sudden you're announcing someone else's prefix. At BGPmon, we've blogged quite a bit about Syria. They've been in the news from an internet perspective because they basically disappeared for hours and days at a time. The whole country would disappear. Obviously, their infrastructure isn't as well established as here. There's a lot of stuff going on, power outages, lots of stuff. So we'd blog about, Syria's offline. They've been offline for 48 hours now. This is awful. But in December and again in January, we blogged about them for a different reason, because basically they now started to claim ownership of about 1,500 prefixes that didn't belong to them. They basically said, oh, I have this route to YouTube and to the US DOD and to Rogers here in Canada. So if you want to send traffic to them, you can send it to me, and I have a really awesome path to it, so you should really use me. So this affected about 1,500 prefixes from roughly 300 different organizations worldwide. The lifetime of this event was typically a few minutes, but some of them tended to last for a little bit longer. And now the whole discussion sort of started. So was this intentional? Was the Syrian Electronic Army behind this, or lots of conspiracy theories? Or was it just an engineer that mistypoed something, which is just as likely? We've seen many of those cases. But obviously, when you mention Syria or China or Iran or Ukraine, it's definitely gets people's attention. So let's take a look at an example. So in this is a visualization of what the internet looked like for one particular prefix at that point, or at least a snapshot. So we're looking at the YouTube prefix 208.117.232/24, normally announced by Google/YouTube. Now it was announced by this ASN 29386, which basically is the Syrian National Telecom Establishment, the main ISP, the only ISP there. So he originated that. It was connected to the next one, 6762, which is Telecom Italia, which is one of the largest ISPs in the world. So if you can make them believe that this route is the best path and really exists, you can be assured that significant portions of the internet will redirect traffic towards Syria. So other prefixes that were affected, DoD, Level 3, YouTube, Telstra, Rogers, Time Warner Cable, Akamai, Telefonica, way, way more than this. But this is just a few examples. And, again, whether this was intentional or not, it's an interesting discussion to have, but from a purely infrastructure or operational perspective, it doesn't really matter. At this point, traffic was being redirected to Syria, and I know that's where it got dropped, because there's no way that they have the capacity to deal with that much traffic from the YouTubes and the Akamais and all that kind of stuff, right? So although it's an interesting discussion to have, as an engineer, I don't really care. As my man, I'm down. And that's how easy it is, unfortunately, in some cases, to bring stuff down. We've seen other cases. Indosat is notorious. They're a large provider out of Indonesia. We've seen it happen several times there as well. So it's really scary stuff. I'm not sure if it was intentional or not. What I will say, though, is it's very easy to hide stuff here as well. Similarly with a DDoS, where people get DDoS and actually some other malicious activity is going on, and it's just a distraction. Same could happen here, right? I could hijack 8,000 prefixes, but I'm only really interested in one. At that point, it's hard to figure out which one I am really targeting and which ones are just noise. But again, we can just look at the data. Can't really see what the intent was here. So one other example, this is a little bit more advanced. It's actually almost the same, but in this case, you're not really re-originating the prefix. You're not claiming ownership, but you're saying, okay, so this is an example from Cloudflare. Cloudflare went down, or had a significant outage in October 2014. I'm not sure if everybody knows what Cloudflare is. It's a very large sort of content delivery network. Some really, really large networks run on it. So if they go down, a significant portion of the popular websites go down. They had an outage affecting many, many of their users in October. Turned out that a provider in Colombia, or I think it was Colombia, basically said, okay, I have this route to Cloudflare. I've learned it through my provider, and now I'm going to re-announce it to my other provider, basically saying, oh, okay, I learned this path, and I'm going to share it with the world. And so the rest of the world can send all this traffic to me. And you can trust me, I will send it back. That's perfectly fine, but it has to come through me. Now, typically, these things are an accident. They're just a leak, a filter that disappears somewhere, or a filter that isn't configured correctly. But again, the same incident also affected AWS. So if you start attracting traffic for Amazon Web Services and Cloudflare, you can be sure that you receive dozens of gigabits, if not hundreds of gigabits. And typically, you know, a regional provider anywhere, in Colombia, in Canada, that is not something you can handle. And as a result, traffic went just, the service for Cloudflare went down. Again, no bad intent probably, still an outage. So, you know, as an operator, you're like, I don't really care what the intent was here. I'm down and we need to fix this. Okay, so quick summary. We looked at a few of the accidents or incidents that were definitely suspicious. We looked at the Bitcoin one, the Turkey one, spamming, Spamhaus, you know, all of those things. I think there's clear indication to at least mark them as suspicious. We also know that some of these things are just fat-fingered. In fact, the majority of them are probably fat-fingered. And then you can argue about if that matters or not, but still it will cause outages. So some of the typical things when we talk about fat fingering is configuration mistakes. When people, this is sort of for the network engineers out there, when you start redistributing BGP into OSPF and then out into BGP again, that's a very traditional way to sort of originate the whole internet. Then there's these things called BGP traffic optimizers that will just make up random new paths and say, you know, you should really use this path, and then they leak it out to the rest of the world. People start using it. There's this technique called AS path prepending, where you can make your path longer. You say, okay, I want it to make twice as long, or I want to prepend my own AS 2 or 3 times. People don't always understand how this works, and they said, okay, I want to prepend it twice. But what you're supposed to do is you have to manually say, basically add a string to it, and you say, okay, this is my ASN, and I'm going to just copy my ASN a few times. You can't, depends a little bit on the operating system that you're using on your router, but a lot of people say, I want to prepend 2 or 3 times. So what it actually shows is the origin AS is 2 or the origin AS is 3. So that looks as a hijack, isn't really a hijack, it's just a fat finger. But you know, there's a lot of these examples. We tend to post them on our blog. How do you deal with this? So there's some work going on in the ITF today around called RPKI, which is really a sort of out-of-band mechanism, that you, sort of a whois, you can think of it, but with some crypto involved that you can cryptographically verify that this prefix really belongs to this guy. And that's something we can't do today, but there's still a lot of work to be done. It's probably years out before people will use it or are willing to use it. So right now, unfortunately, the real answer is, you know, you have to watch for these kinds of things. There's monitoring services out there, commercial, free, you can roll your own, but that's really the only thing you can do today because you have to know that these things happen. I've had users tell me that, you know, we just stopped seeing traffic coming in. So I would reach out to them and say, hey, did you know this happened to your network? Someone rerouted your traffic to Latin America. And they would be very skeptical, and they said, well, who are you? Like, I would just, you know, as a courtesy, reach out. And then they would say, no, as such, you must have seen an outage based on all this data. You know, you must have seen an outage. Like, no. Okay, so I would explain them, and after 10 minutes, they say, okay, you know, I might as well be truthful. You know, we did indeed see an outage. We looked at all of our firewall logs, VPNs, IDS, blah blah blah, and nothing showed up. And that was the case because the traffic just wasn't there. The traffic was being sent somewhere else. So it was a really interesting example of where some of these, very advanced security teams just, didn't click in that traffic could have just rerouted somewhere else. So it's definitely something to keep an eye on because, you can't log what you don't see. Anyway, so that's sort of a summary of what's going on in the world of routing. Some cool examples, and yeah, let me know if you have any questions, feedback.